Welcome back to Mining of Massive Datasets. In the previous lectures, we studied the basic MapReduce model, and then we looked at how it's actually implemented. In this lecture, we're going to look at a couple of refinements to the basic MapReduce model that can make it run a bit faster. The first refinement we're going to look at is combiners. Now, one of the things that you may have noticed in the previous examples is that a map task will produce many pairs of key value pairs with the same key. For example, a popular word like the will occur in millions and millions of key value pairs. Now, remember that the map tasks are actually happening in parallel on multiple worker nodes, and the key value pairs from each map node have to be shipped to reducer nodes. If you sort of imagine a word like on node 1, map task 1 is probably going to see a few thousand occurrences of the word the, and map task 2 is going to see a few thousand occurrences of the word the, and so on. And so the output of map task 1 will have, let's say, 1,000 tuples with the key the and the value 1. Now, all these tuples will have to be shipped over to, let's say, to reduce task 1. Now, shipping 1,000 tuples over, all of whose keys are the and all of whose values are 1, is a lot of network overhead. And you can save some of this network overhead by doing an intermediate sum in the map worker. For example, instead of sending 1,000 tuples that each say that each have the key the and the value 1, you can send a single tuple that has the key the and the value 1,000. Right? And so you can save a lot of network bandwidth by doing a little bit of pre-aggregation in the map worker. Here's a mapper, and the mapper, this is our word count example again. The mapper he has B occurring once, C occurring once, D occurring once, E occurring once, D occurring once, and B occurring once again. And now the tuple B occurs 2 times here, as in the output of this mapper. So like the combiner, which is another function that is provided by the programmer, combines the 2 occurrences of B and produces a single tuple B, 2, which is then shipped over to the reducer. So instead of 2 tuples of the form B1 being shipped over to the reducer, a single tuple of the form B2 is shipped over to the reducer. And this way, much less data needs to be copied and shuffled. So the combiner is actually also supplied by the programmer. The programmer provides a function combine. The input to the combiner is a key and a list of values, and the output is a single value. So instead of a whole bunch of tuples with the key k being shipped off to a reducer, just a single tuple with key k and value v2 is shipped off to the reducer. Now, usually the combiner is the same function as the reducer. So if, for example, if the reducer adds up its input values, the combiner does the same thing as well. However, we have to be careful because this trick of using the combiner works only if the reduce function is commutative and associative. Let's look at a couple of examples to see what I'm saying here. So for example, let's say the reduce function is a sum function. You want to add up all the input values, as in the count example. Now the sum function actually is commutative and associative, by which we mean that a plus b is the same as b plus a, and a plus b plus c is the same as a plus b plus c. This is the first property is the commutative property, and the second property is the associative property. And because sum satisfies both these properties, sum can be used as a combiner as well as a reducer. What that really means is that if you have a lot of values that need to be summed, all these values need to be added up. You can break it up into 2 pieces. You can sum up the first piece, you can sum up the second piece, and then you can sum up the 2 intermediate results, and you'll get the same answer, right? So And so this is the first combiner sums up this first chunk of outputs. The second combiner sums up the second chunk of outputs. Then you sum up the two intermediate values, and you get the same result as if you had summed up all the original values to begin with. So that trick works because sum is commutative and associative. However, there are some functions that are not commutative and associative. An example might be average, right? Let's say the reducer needs to compute the average of its set of input values. So the set of input values consists of a key followed by a bunch of values. And the combiner, the reducer, needs to find the average of this set of values. Now, let's say we divide this set of values into two sets, compute the average of this set, compute the average of this set, let's say that's average 2. And now we take the average of average 1 and average 2. That's the average of average 1 and average 2. Now it turns out that this is actually not the same as the average of all the values that are out there. So the average function, as we have seen, is not commutative and associative, and so you can't use it as a combiner. But it turns out that you can still use the combiner trick if you're a little bit careful. Instead of using average as your reduce function, if the reduce function instead outputs a pair which consists of sum and count, okay, then the average can be computed in one extra step. It's just a sum divided by the count. So if the combiner, instead of sending the average of all its values, let's say the key and values, and here are the chunks. Now the combiner, the first combiner computes the sum of this piece and the count of this piece. The second combiner computes the sum of this piece and the count of this piece. And the third combiner computes the sum of this piece and the count of this piece. And finally, all these values, the sums and the counts, get shipped to the reducer. And the reducer computes a final sum, which is a sum of the intermediate sums it has received, a final count, which is a sum of all the counts that it has received, and divides the sum by the count, the final sum by the final count. That, in fact, turns out to be the correct average. Right? So using this trick of using sums and counts, it's sometimes possible to turn a function that's not commutative and associative, break it down into functions that are commutative and associative, like sum and count, and still use the combiner trick to save some network traffic. Unfortunately, it turns out that while most functions are amenable to the combiner trick, there are some functions that don't work with the combiner trick at all. One example is median. Right? The median of a set of values is obtained by sorting, obtained by sorting that set of values and then finding the middle value in that sorted list. It turns out, and it can be proved mathematically, that there is no way to split the median computation into a bunch of commutative and associative computations. So you can't actually use the combiner trick if your goal is to compute the median of a set of values. You just have to ship all the values to the reducer and compute the median at the reducer. The next refinement we're going to look at is the partition function. Now, remember that the MapReduce infrastructure uses a hash function on each key in the intermediate key value set. And this hash function decides which reduce node that key gets shipped to. Right? The MapReduce system uses a default partition function, which consists of hashing the key using a predefined hash function, and then taking the result modulo r. Now, this gives a number from 0 to r minus 1, which decides which reducer the key is sent to. Now, sometimes you may want to override this partition function with a custom partition function. For example, we might want to ensure that all the URLs from a given host, let's say, end up in the same output file and are therefore sent to the same reducer. So instead of hashing by key, you might want to hash by the host name of the URL. And the MapReduce framework allows you to specify a custom partition function that can do things like this. The initial implementation of MapReduce was done at Google. And Google first implemented a file system called the Google File System, which is a distributed file system that provides stable storage on top of its cluster, and then implemented the MapReduce framework on top of the Google File System. Google's implementation of MapReduce is not available outside of Google. Hadoop is an open source project that's a reimplementation of Google's MapReduce. It uses a file system called HDFS for stable storage, and it's implemented in Java. Hadoop is an Apache project, and you can freely download it from the Apache website. It turns out that many use cases of Hadoop involve doing SQL-like manipulations on data. And so there are open source implementations called Hive and Pig that provide SQL-like abstractions on top of the Hadoop MapReduce layer so that you don't have to rewrite those as map and reduce functions. Let's finally wrap up by looking at MapReduce in the cloud. Amazon's Elastic Compute Cloud, for example, is one example of a service where you can rent computing by the hour. And Amazon also has an implementation of MapReduce called Elastic MapReduce that you can run in the cloud. This concludes our discussion of MapReduce.